boy Mentor the Great. If you are new here, click on the subscription button, ring the bell so that click on the bell button so that you will be the first to receive any notification of every video I'm going to post. You will get notified that the video has dropped, and then like, comment, and share my video. Today we are, as I told us in the other video I made before now. If you've not watched the previous video where I talked about fundamental and derived units, for you to catch up very well, you go through that. But today we have dimension analysis. Firstly, by definition, we're going to define dimension of a physical quantity. Don't forget, if there is any question you have, make sure you put it down in the comment section so you can go through it. If there is any topic you find it difficult, just put down the topic at the comment section so that the next video we're going to tackle it. And if there is any questions, still drop it on the comment section. All right, dimension analysis. Dimension of a physical quantity is simply how these quantities are related to the dimension of the fundamental quantity. So when you talk about dimension of a physical quantity, for instance, dimension of force, then if you want to know dimension of force, it has to do with, you are interested to know how force is related to the dimension of the fundamental quantity, that is the dimension of mass, length, and time. In dimension analysis, you make use of M, L, and T. When you talk of dimension of acceleration, you want to know how acceleration is related to mass, length, and time. So we say dimension of any physical quantity is how these quantities is related to how these quantities are related to the dimension of what? Mass, length, and time. Let's say dimension of a physical quantity is defined as how that quantity is related to the dimension of the fundamental quantity. The fundamental quantity. And of course, fundamental quantity in this aspect will mean the mass, the length, and the time. So of course, we already know we are going to tell you guys what we mean by dimension of mass, length, and time. So we have the fundamental quantity we are talking about here. Fundamental quantity, and dimension. We say that the dimension of a physical quantity is how that quantity is related to the dimension of mass, length, and time. So what is this dimension of mass, length, and time? Watch out. Mass, the dimension is capital M, just the first letter. Then length, the dimension is the first letter, which is L. Then time, the dimension is capital T. So whenever we talk about dimension, we can't talk about the dimension without making reference to mass, length, and time. We always refer to mass, length, and time. So that's why anytime we talk about dimension, any place, anywhere you see dimension of any quantity, it has to do with mass, length, and time. You just want to know how is this quantity related to mass, length, and time. That's the dimension of that particular quantity. Okay, without wasting much time, I want us to take a note. There are other quantities that have this relationship. That have this equality, like the likes of height, width, breadth, extension, wavelength. All these quantity dimension now, they are dimensioned as length, L, displacement, distance. Just watch out. Note. Height, breadth, or width, anyone, breadth or width, then distance, displacement, extension, wavelengths, anyone, wavelengths. That's the one we use that to know. Of course, there is any other quantity, altitude, etc. All the quantities that you know that has meter as its unit. The dimension of any quantity that is measured in meter is length. So anywhere all these quantities appear in any physics mathematical formula, you use length as the dimension. So just take it down. It's a very important note when it comes to dimension analysis. So anywhere you see all these quantities I mentioned now, you know that their dimension is L. Just use L as the dimension, L. Okay, they have a dimension of length. L has the dimension of length, L. Whenever you see them, you put L as the dimension. Okay, let's look into some dimension. Let's look into some dimension. Examples. Compute the dimension of the following. Compute the dimension of the following. We have A. Let's have let's start from the little. We have area. B, we have volume. Of course, let's take on these two. We have density. We'll take on the first three derived quantities. Let's know the dimension. Solution. Of course, area. Of course, let's know the formula for area first. The area is length times breadth, but by dimension, breadth is measured in meter. So, of course, from what we stated here, breadth should have a dimension of length. So, the dimension of length is length, dimension of breadth is also length, so that the dimension of area becomes length squared. So the dimension of area is length squared because we are multiplying two quantities whose dimension is length. So we're having length squared as the derived as the dimension. Then B part of it we have the volume. The volume is the length times the breadth times the height. In this case, we are multiplying three quantities whose dimension is length. From here we say height, breadth. Both of them has a dimension of length. Therefore, length times length times length. Definitely we have length times length times length. So that the dimension of volume becomes length cubed. Last but not the least is the density. Density is firstly density is mass over volume. Mass over volume. But don't forget, we hear the dimension of mass is M, capital M. And of course, this is just the formula for density. Then we will have the dimension. We have the dimension we say equal to, the mass is capital M. Of course, we already had volume, and what we had in volume is length Q. Of course, the dimension of volume, we are going to transfer it there. We have length Q, so that the total dimension of density is ml raised to the power minus 3. So when you bring the L cube, when you take it up to join this M, you are going to use a negative. This negative shows that the factor is coming from the denominator, and for it to have to be in the same plane with M, it has to do minus 3 as the power. So that's the dimension. Of course, here as an omission, there should be dimension. Let's correct it. Then this is also dimension equal to. So dimension of area is length squared, dimension of volume is length cube, and that of density is meter length raised to the power minus 3. Watch other examples. We have velocity. Of course, velocity is displacement over time. But by dimension, of course, dimension of displacement is among the ones we say it is dimension is length. So dimension of displacement is length L. The dimension of time is T. From what I told you guys here, of course, displacement is among what we talk about here. So the displacement has a dimension of length. So that's why we remove displacement and put length there. So dimension of time already we know is length. So this is equal to L. Taking this T up, because it has no power, it has to be T. Definitely it's minus 1. But if there is 2 here, then if you're coming up here, it should be minus 2. That is the negative index law of indices in mathematics algebra. Okay, the next is acceleration. Acceleration is velocity over time. Of course, by dimension, velocity is already Lt minus 1 over, that's another time, and the dimension is T. Of course, the T coming up here, it's going to join with that minus 1. So another minus 1 will enter, and then the power will now be Lt minus 2, so that the unit of the dimension of acceleration becomes Lt minus 1, and the dimension of velocity is Lt, acceleration is Lt minus 2, and that of velocity is Lt minus 1. So the difference is velocity is minus 1, then acceleration is minus 2. Alright, the next one I want us to look into is momentum. Momentum is product of mass and velocity. Momentum is the product of mass and velocity. Of course, by dimension, how momentum is related to mass, length, and time. Of course, the dimension of mass is a capital M. The dimension of velocity is already here, Lt minus 1. So definitely we have Lt minus 1. That's multiplying mass and velocity. So this is the dimension of the so-called momentum. Alright. This other technical examples, not only technical but the advanced form of what we just treated here. Let's see what we have here. Core. For what respective values of x, y, z will the dimension of force be equivalent to m raised to the power x, l raised to the power y, and z, and t raised to the power z. So what respective values of x, y, z with the dimension of force be equivalent to this? So we're going to find the dimension of force and then look on them, watch on the powers of the m, l, and t. They will correspond to x, y, z. That's very simple to do. Then let's get to it. Solution. Right. So firstly, force is equal to mass times velocity. Of course, we all know mass is capital M by dimension. By dimension, mass is M times velocity is L t minus 1. Then upon multiplication, we're going to have M L t minus 1. So if this answer is equivalent to what we are given here, which is M to the power of x, L to the power of y, and t to the power of z. So one can intuitively state clearly that the power of m here is 1 and the power of L here is 1 because it has no visible power. Definitely it has a power of 1. So by comparing the powers from both sides, it is evident that x is equal to 1 and y is equal to 1 and z is equal to minus 1. So the respective values of x, y, z are 1, x equal to 1, y equal to 1, and z equal to minus 1. Equal to minus 1. Okay, let's talk about this last example. I want to talk about is the gravitational constants. Let's find the measure of gravitational constant. So let's talk about gravitational constants. Gravitational constant, capital G. Of course, gravitational constants, we can get it from gravitational field. That's force of attraction between two masses in a gravitational field. Of course, from the relation F is proportional, that's F is equal to G m1 m2 over r squared. That's the force of attraction between two massive bodies in a gravitational field. Then let's make G the subject of the formula. Then making G the subject of the formula, G is equal to F r squared, then divided by m1 m2 m1 m2. So that is the formula for the gravitational constant. So by dimension, the dimension of force, definitely we've already seen the dimension of force there, so we can quickly align and see the dimension of force there is mass times velocity and mlt minus 1 times, of course, r means radius, and radius is measured in meter, and of course any quantity that is measured in meter must be dimensioned as length. So radius, the dimension of radius is equally length. So r square is length square all over the dimension of mass is still capital M. The dimension of another mass is capital M. So from what we have there, equality up and down, M can cancel M, and then when we bring M, this M is surviving in the denominator. If you are to take it up, we're going to have M power minus 1, then L multiplied by L will give us L cubed, then T minus 1. So, and that is the dimension of gravitational constant. So, this is the end of examples on dimension analysis, but the next thing I will get to now is how to use dimension to know the correctness of an equation, to know if an equation is correct. The use of dimension to verify the correctness of an equation. That's the next. Catch it up in the next video. The use of dimension to show the correctness of an equation. An equation is said to be correct. An equation is said to be dimensionally correct if all the terms involved in the equation have the same dimension. It's dimensioned exactly the same. So we're going to look into one or two examples and show how they are dimensionally correct. So the first one, V is equal to U plus AT is the first equation of motion. So let's verify if this equation is dimensionally correct or not. Then what's the dimension of velocity here is Lt minus 1, as we know already, and dimension of initial velocity is same thing as velocity. So the dimension of the velocity here is equally Lt minus 1 plus the dimension of acceleration is Lt minus 2. Forget not or view the previous video and you see when we dimension acceleration as Lt minus 2. Then time is t. Then simplifying further, we have Lt minus 1 equal to Lt minus 1 plus L. Then t is here and t is here, but in this is like t raised to the power 1. And then, of course, so we take one of the t and we'll add up the powers. We have minus 2 plus 1. Finally, Lt minus 1 is equal to Lt minus 1 plus Lt minus 2 plus 1 is minus 1. So, as you can see, it is evident that all the terms, both the terms before the equality sign and after the equality sign, we have three terms in this equation. 1, 2, 3 has exactly the same dimension. Definitely the equation is dimensionally correct. Let's check in the next one. V square is equal to U square plus 2ax. Let's know if this equation is still dimensionally correct. Forget about the constant 2 here. It doesn't count. What we're interested here is the quantities and their dimension. So watch out. Velocity is still Lt minus 1, but it is squared. So we have all squared equal to. Then the initial velocity is Lt minus 1 also, all squared equal to 2, that's plus. Acceleration is Lt minus 2, and the distance, S is the distance, and distance is dimension as length. So the dimension of distance is length. So we have times length. So that here we're going to use the indices, the power outside multiplying the powers inside. Of course, the power here is going to affect L and T minus 1. So when the power comes here, we have L squared t 2 times minus 1 is of course minus 2, and the same thing happens here. We have L squared t minus 2 plus, that's 2 of course, L times L is L squared, and of course t minus 2. So regardless of these constants, it's evident that all the terms both in the left hand side and the right hand side contain exactly the same dimension. Therefore, the equation v squared is equal to u squared plus 2as is dimensionally correct. Here I will end this video on dimension analysis. So we're already done with the fundamental and derived quantities. We've achieved that, and we achieved dimension analysis. Then the next video, definitely we're going to enter into motion, different types of motion, and equations of motion. That's position, distance, and displacement. Thank you, and don't forget, if you have any question, just ensure you drop it on the comment section so that in the next video we're going to tackle it. Then if there is any topic you find it difficult to understand, still drop the topic there and we'll ensure to give you an enlightenment on that. Thank you and stay tuned.